Ruby, we're back. All right, so we've just finished proving that every compact set is closed and bounded. Now we need the opposite. Every closed bounded set is compact. So let's do that. I guess there's one thing that's missing. Let's assume the set C is closed and bounded. That's one thing that I'll need to add back to the actual notes. That's important. We need to show that the set is compact. Thus, we need to show that, well, what does compactness mean? It means that for every open cover of C, there is a finite subcover. All right, so there's what I need to do. That tells us something about the structure that the proof's going to need to take. We need to consider any open cover of C. I need to show that this math_cal F has a finite subcover. And I think it's worth taking a tour of like the structure that this will have. So let's let X be the set of all X in R such that not all of C, but just everything in C up to X is covered by a finite subset of math_cal F. So I'm going to add a quick blank page after it. So X in this set big X means, right, you have this, there's all the real number line. Here's the set C. Maybe it has like a limit point right there that it achieves. Maybe it has some little closed intervals in it. Maybe it's got like a piece that looks like the Cantor set. Look up that if you've never seen the Cantor set. You should do it. X and X means, so if there's all of C, if there's X, that means that if I look at all of the stuff in C up to and including X, I guess only include X if X is actually in C. Is covered by a finite subset. Sorry, let me pause this. And we're back. Is covered by a finite subset of F. So remember what that means. F is like a union of a bunch of open sets. So it's a bunch of open sets so that when I consider the union of a lot of them, I cover up all of C. And if I only want to get everything up to X, I can use only finitely many. That's what it means to be in the set big X. So the set big X is going to have an interesting role. Let's see how we're going to use it. So first of all, I'm going to show that X is not empty. Well, why should X be non-empty? Well, if X is not empty, well, let's see. What do I know? I know C is bounded below. Let's just use that it's bounded below. So if there's like this lower bound L, then everything in C is to that side of L. There's an upper bound too. Now if I take like that X, an X that's less than L, then there's nothing in C. Oh, and you don't need many things to cover the empty set. Let's see, I need a finite subset of F that covers C. All right, that's very informal, but let's put those details together. X is not empty. The set C is bounded below by assumption. Let's let L be a lower bound. I need to show that L minus 1 is in X. First, notice that this is equal to the empty set. Let's explain why it's true. Well, maybe proceed by contradiction. By contradiction, let's suppose negative infinity to L minus 1 intersects C is not empty. So there exists, I don't know, C in C intersect negative infinity to L minus 1. And if we're going to put things in that order, let's put things in that order. You don't have to change your notes, but it's easy for me to change it, so let's do that. Oh, wait. But then C is in C, and C is less than or equal to L minus 1 is less than L. So L is not a lower bound. That's a contradiction. All right. All right, so this thing is empty. So that means we don't need to use any elements of MathCalF to cover this thing. Thus, the empty set is a finite subset of F. And let's just check that. The empty set is a finite subset. Yeah, the empty set's a finite subset of everything. Does it still cover? Yeah, there's no elements in that thing to cover. So let's see, as there is a finite subset of X, nope, of F, namely the empty set, which covers C intersect negative infinity to L minus 1. L minus 1 is in X. So X contains something, so it is not empty. All right, so here's how we're going to proceed. We are now going to show that X is not bounded above, and let's see why that would be cool. So this isn't like the proof that X is not bounded above. Let's see what would happen if X is not bounded above, then there exists some X in X such that X is bigger than the supremum of C. And I don't really care that that's the supremum, I just care that it's an upper bound. Oh, wait, that's interesting. But then all things in C are less than or equal to X. This is very informal, so that's okay writing. So C intersect negative infinity to X is equal to just C. Ah, but then by the definition of X, this thing is covered by a finite subset of F, which is what we want. That would do the job. So let's do that. Let's show that x is not bounded above. So let's assume for the sake of contradiction that x is bounded above. All right, standard proof by contradiction stuff. Well, let's see what that'll get us. Well, I already know x is not empty. If it's bounded above, then it has a supremum. So it's let S be the supremum of the set big X. And there are going to be two different cases. Either S is in C or it's not in C. In each case, I'll get a contradiction. These two contradictions are detailed in steps 2A and, well, there's my scratch walk, 2B. And in fact, what I might encourage you to do is this. Pause the video, try to figure out what's going to happen in steps 2A and 2B, and then come back. Cool, you did that. Let's see if I agree. All right. So step 2A, let's suppose that S is in C and get a contradiction. In fact, here's the contradiction that I'm going to get. I'm going to show that S is not an upper bound on X. And that tells you like how I'm going to do that. I'll find a thing in X that's bigger than C. Ooh. All right, so let's try to do that. S is equal to the supremum of X is a subset of C as math_cal_f is a cover of C. Let's see. I'm going to add another blank page to keep on thinking on this. So let's draw another picture. So here's S, which is the supremum of this set X. And right now I have that this is in the set C. And what's going to happen first? Well, F is a cover of C, so some element of F has to contain that S. Right? That's what it means to be an open cover. Let's make that a little bigger. And I've drawn it like this because I know V is open. So S has to be interior to V. So there's definitely some open interval, the thing that I've just drawn in blue, that contains S and is contained in V. So let's detail that. Since V is open, there's some epsilon bigger than 0, so that S minus epsilon to S plus epsilon is contained in V. All right, so I know the picture is on the next page, but let's see it. So there's this S. That blue thing is S minus epsilon to S plus epsilon, and that blue thing is a subset of V. That V is an element of math_cal_f. All right, so I know that S is the least upper bound on X. That's what it is by definition. Let's use that. So that's the least upper bound on X. So this thing is less than S. So this thing is not an upper bound. So there must be some little x in the set in between the two. All right, so let's write that out. Since S minus epsilon is less than S, and S is the least upper bound, there's some x in x so that s minus epsilon is less than x. Ooh, but let's remember what that means. What's the definition of the set big X? The set big X is all of the elements of the real numbers, so that if you take C and you only look at things to the left from X, including X, what you get is covered by a finite subset of MathCal F. All right, that's a lot, but that definition just says if I only take things in C that are to the left of X, that is covered by some finite subset. As X is in X, the definition of X implies that there's some finite subset, G sub X. It depends on what X is, so it's reasonable to call that G sub X, which satisfies that G sub X covers C intersect minus infinity onto this X. All right, very nice, very nice. So, pictorially, let's see what that means. There's space for a reasonable picture. Let's draw the picture here. So here's that same number line. There's S minus epsilon. There's S. There's S plus epsilon. That stuff in blue is a subset of V. Here's X. Negative infinity to X. If I intersect that with C, that's covered by G sub X. Wait. So what if I want to take a number here, like S plus epsilon over 2? Let's try to convince ourselves that that's also in the set big X. Let's see. Let's maybe think case-wise. So if I consider anything that's in C and in that open interval, then either it's over in this interval and is covered by stuff in GX, or it's in this range, but things in this range are in V, where recall V is like that open set, the one that we got because S was an element of one of the elements of MathCal F. Oh, wait, but then that means GX together with the set containing V. And, well, those set prices are important, as I'll talk about in a moment. Well, that covers this. Wait a minute, but that means that S plus epsilon over 2 is in this set X, but it's bigger than S. There's a contradiction. I found something in the set big X that's bigger than the supremum. So let's write down those words. Let's explain why GX, together with the set containing only V, so remember, a cover is a collection of a bunch of open sets. So an element of an open cover should be an open set. If I take GX, sorry, I need to use the pointer. If I take GX union V, well, any element of V would be in there. An element of V is not an open set, so I need set braces around those V to indicate that I'm just adding a single element to GX. That single element is V. That covers. All right. So, how is it that we did that? I guess it was like a case-wise analysis. Let's do those case-wise analyses. So let's consider any C in C intersect negative infinity to S plus epsilon over 2. So C is in C, and C is less than or equal to S plus epsilon over 2. If, additionally, C is less than or equal to X, then C is in some element of Gx, and we're done. Why are we done? Well, what does it mean to cover? Every element of that set needs to be in one of the open sets in this collection. Things in Gx, yeah, they're in that collection. So we may as well assume X is less than C, but then let's scroll back down and use the ideas here. So that means X is bigger. Nope, C is bigger than X, so it's in like this range. So it's in between X and S plus epsilon over 2. But X is less than S minus epsilon. S plus epsilon 2 over 2 is less than S plus epsilon. So it's actually in this blue interval. That's a subset of V. All right. But then what do we have? X, let's just list all the inequalities. But then S minus epsilon is less than X. By that is less than C, is less than or equal to S plus epsilon over 2, is less than S plus epsilon. So C is in S minus epsilon to S plus epsilon, but that maybe but's the wrong one, because S minus epsilon to S plus epsilon is a subset of V. This means C was the name of it? C is in V. Well, but V is definitely an element of Gx together with singleton V. Either way, we get Gx union singleton V covers C intersect negative infinity to S plus epsilon over 2, as we have now constructed a finite subset of MathCal F covering C intersect negative infinity to S plus epsilon over 2, S plus epsilon over 2 is in the set big X by the definition of big X. This is a contradiction, as S equal to the supremum of X is required to be and upper bound on big X. Nice. All right. So that contradiction deals with case 2A. If S is in C, then we've gotten a contradiction. So it must be that S is not in C. Whew, let's do it. And again, if S is not in C, we will show that S is not an upper bound on X. And this time, we'll use that C is closed. Since S is not in C and C is closed, S cannot be a limit point of C. Ooh. And let's remember, what does it mean to not be a limit point? That means it is not the case that for every delta bigger than 0, there exists a C in C minus singleton S. I haven't used any coarse of S's yet, so no need to start right now. Such that absolute value C minus S is less than delta. And I negate it. You negate a universal, you get an existential. So there exists a delta bigger than 0, such that there exists a C, such that for all C in C minus singleton S, not this happens. Absolute value of C minus S is bigger than or equal to delta. All right, cool. All right, well, let's do it. Since C is not an S, C is closed, C cannot be a limit point. So, well, it says I want an epsilon, so in order to match up with the notes, I'll get an epsilon, even though this is a delta. It doesn't matter what you call it. So, there exists a delta bigger than 0, such that for all C in C minus singleton S, what am I doing? Absolute value C minus S is bigger than or equal to delta. So I'm going to, like, again, go to this next page, add a blank sheet. Oh, there's already blank space there. Let's write down what that means. Yeah, I got space right here. This isn't like part of the proof, but it's worth seeing to like motivate what's going to happen next. So here's this S. There's, oh, I said I'd use an epsilon. There's S minus epsilon. There's, oh, that should be S plus epsilon. There's S minus epsilon. There's S plus epsilon. In this range, for all C in C minus S, the absolute value of C minus S is bigger than or equal to epsilon. So, open endpoints. No stuff in C here. Because remember, like, you might worry, oh, what about S? S could be in there. Oh, but S is not in C by assumption. So again, that minus S doesn't actually do anything for us right now. As before, S minus epsilon is not an upper bound on X. So there's some X that's bigger than S minus epsilon has to be less than S because of the fact that S is an upper bound on the set big X. S is the supremum of big X. As before, since S minus epsilon is not an upper bound on big X, there's some little x in big X with S minus epsilon. Sorry, less than X. And remember the definition of X. So there exists a finite subset G x of f, which covers C, it's not squiggly C, just normal C, intersect negative infinity to x. So G covers stuff in C that's at most x. Wait a minute, but if I move this x up some to like there, well, there's not allowed to be anything in C in that range, right? So I don't actually increase the size of C intersect bound if I move that x plus, as long as I don't go past s plus epsilon. Ooh. So I think that means that the same set covers. So I guess said a different way, gx also covers negative infinity to s plus epsilon over 2, close bracket, intersect C. All right. So I think I'm getting real close. I think I'm basically there. Let's push on a little bit longer. So what does it mean to cover? Well, let's consider any C and C intersect negative infinity to s plus epsilon over 2. Well, let's use this fact. As C intersect s minus epsilon to s plus epsilon equals the empty set, little c cannot be in s minus epsilon to s plus epsilon. Maybe that's the wrong way to think of it. Let's go back a little bit. You can definitely follow those ideas. So let's see. How about this? For contradiction, suppose C is bigger than little x, but then as C is in negative infinity to s plus epsilon over 2, negative x is less than C, sorry, is less than or equal to s plus epsilon over 2. Well, s plus epsilon over 2 is definitely less than s. And let's remember, s minus epsilon is less than x. Oh, and hopefully I didn't say negative x right there. S plus epsilon. So C is in s minus epsilon to s plus epsilon. This contradicts that C intersect s minus epsilon to s plus epsilon is the empty set. So what did we assume for the sake of contradiction? We assume this. So C is less than or equal to x, but then C is in, well, it's still in the set big C, intersect negative infinity to x, which is a subset of the union over things in Gx as Gx covers this. This is too big. C intersect negative infinity to x by assumption. All right, so that was a lot, but what did we achieve? We achieved this. Since we now have Gx covers C intersect negative infinity to s plus epsilon over 2. Let's remember what the set big X is. The set big X is all of the x's, so that if I take everything in C and intersect it with negative infinity to x, that thing is covered by a finite collection of f. Gx is a finite collection of x, and it covers negative infinity to s plus epsilon over 2. Thus, s plus epsilon over 2 is in x, contradicting that s is equal to the supremum of big X. All right, so let's remember what we were doing. So we got a contradiction now if s is not in C. So now we got a contradiction if s is not in C and a contradiction if s is in C. That means s just cannot exist. So we have just demonstrated that x cannot have a supremum. But x is not empty. Every set that's not empty and bounded above has a supremum. That means this set x could not have been non-empty. So x is not bounded above. Let's now wrap up the proof and get our end result. We assume that C is bounded above. Let's let U be an upper bound on C. Is it possible that U is an upper bound on X? Nope. X has no upper bound. Now wait, but that means that there's some X in X with X bigger than U. And let's remember the point. That's going to bias that X is bigger than C for all C in C. By the definition of X, then, C intersect negative infinity to X is covered by some finite subset of mathcal F. Wait, but as X is bigger than U and U is bigger than or equal to C for all, you know what? It's a set equality proof. Let's compose it as a set equality proof. No need to be lazy. Let's see. If Q is in C intersect negative infinity to X, then Q is in C. Yeah, let's just say by properties of intersection. On the other hand, if Q is just in C, then as U is an upper bound on C, Q is less than or equal to U, but remember U is strictly less than X. So Q is in negative infinity to X. And I could put an open bracket there, but close bracket will get me what I actually need. Oh wait, but it's in C and it's in there, so Q is in C intersect negative infinity to X. Thus, C is equal to C intersect negative infinity to X. Wait, now let's just wrap it up. But I don't need to remind you that it's by the definition. Um, oh no, I do have to use state Y. Okay. By the definition of big X, C, which is equal to C intersect negative infinity to X, is covered by a finite subset of squiggly F. Wait, what have we done? Let's put it all together. At the start of the proof, we considered any open cover of C. By doing all this jiggery pokery, we have now constructed a finite subset of that same open cover, which still covers C. So C is compact. Neat. That's like a really fun, sneaky proof of this claim. Um, and with that, I'll stop. I'll see you all on Wednesday. I hope you enjoyed this.